My name is Moshiko Emmer. I'm leading the Chiplets R&D in Cadence. I will be accompanied by Sylvain Guy from SoC, and we will present to you how we revolutionize SoC design with chiplets. All right, so we'll talk a little bit about the industry strengths, what we hear from customers, what are the main challenges, specifically in automotive, but not only. We'll talk a little bit on how the journey of SoC designer is moving from a monolithic design into the world of chiplets. I'll go over the main value proposition of chiplets, what we call the 4 C's of chiplets. And then we'll dive into how we are offering to accelerate SoC design in automotive through chiplets. We'll have some part on the security, how SoC fits in, how we build security into chiplets. Sylvain will cover that, and we will end up with looking at how our end-to-end approach from Cadence can help you work with chiplets. Okay, so we see today different industry trends that are all kind of coming together to the picture that we see that creates both the challenge as well as the opportunity for chiplets. First of all, we see growing usage of disaggregation, taking a design, splitting it to multiple chiplets, thanks to the advances on package technology, on package tools, and the ability to actually split a design into different dies, not necessarily on the same process technology. We see many companies looking more into solutions, not focusing only on IP. There is a lot of thinking of how I can differentiate what I want to bring. It is very understood that as these products become bigger, more complex, the ability of a single company to bring an entire solution is more challenging. So you want to probably focus on your secret sauce, on what differentiates you, looking more at the solution level. There is a growing interest in customizing the silicon, not using just a general purpose silicon that it can be used for any usage. We understand that there are different types of computes that are needed for different types of applications. And obviously, the fact that the foundry offerings, the foundry options are growing, creates a lot of opportunity to potentially integrate multiple solutions from different foundry or within the same foundry between different technologies. So what do we hear from customers about what is their problem statement? We hear a lot about cost efficiency. How can we build systems that are more cost effective? When we use monolithic systems, the ability to optimize the price and the cost efficiency is more limited. To bring different types of compute usually means to rebuild an entire SoC on a different process technology with different set of IPs and so on. It is somewhat limited, it's very expensive. The time to market in a new solution is hard. I want to refresh an existing product and create a derivative, maybe even the same architecture in a new process technology. The time to market is very long. I need to rebuild all the IPs, I need to qualify them in the labs before I can sell them. It also translates to money, but the time to market becomes longer. And obviously, when we are looking today at the number of distributed systems we have, automotive is a good example. Having so many compute components makes the software development, the software verification, the software management very complex. And this is something that customers are asking to see how we can simplify. In terms of design, in the past, the trend was to puts more and more functions on the same monolithic SoC. It started with CPU only. With time, memory was added, and then AI function, DSP, of course, many types of interface IPs and IOs. And design started reaching both the reticle limit, so designs became too big to fit on a single silicon die, as well as too expensive. Because if you want to have a chip on a latest and greatest process technology, a very advanced one, it means that you also need to migrate all your IOs to that same process technology, which is challenging. Companies started looking at building multi-die SoCs, splitting the problem into separate dies. Each of them may be limited by the reticle size, and then integrate them together. And today, with the chiplet technology and the ability to package different chiplets on the same package, we can have better usage of that by splitting the chiplet based on the functionality and have separate dies, separate chiplets, each of them focused on specific functionalities, integrated together on the same package, thanks to the advancement on the package side. Our 4 C's of chiplets is how we believe you can understand the value proposition of chiplets. So the first C is the cost efficiency. You can reduce the design time and the cost when you use chiplets, because you can build a system where, let's say, you have several chiplets on that system. Some of these chiplets you leverage from a partner. Someone else who has the expertise is building that chiplet for you, and you focus on the area where you differentiate, where you have the expertise, where you can bring your value. You don't necessarily need to invest in developing all the compute functions that were needed before. The second C is the customization. With chiplets, you can build modular and scalable systems from the same set of chiplets. So in this example, we show how you can build with a relatively small set of chiplets, different systems from low end through mid-range and to high end. So in the low end, I don't know if you can see from there, but in the low end, we have a CPU chiplet, a GPU chiplet, a system chiplet which contains most of the IOs, memory, and so on, and maybe an AI dedicated chiplet. And as you scale up, you can add more functionalities, like adding multimedia and DSP on the mid-range, or even duplicate the CPU and AI chiplets on the high end. So this way you can bring a wide range of products based on reusing the same chiplets that you designed across the system. Obviously, if you do that, you need to make decisions. Like the system chiplet is common to all these systems. So you need to decide whether you want to have 3 optimization points for the system chiplet for each of these, or you want to design a single system chiplet that will have some inefficiency in optimization, but on the other hand, you can completely reuse it in the entire stack. The third C is the configurability. As I hinted earlier, with chiplets, you can decide that from generation N to generation N+1, you only refresh part of the system. You don't have to redesign, remanufacture the entire silicon. You can say, I will replace, for example, the CPU component with a newer chiplet on a new process technology, or maybe with more cores, while I will reuse the entire stack, and this way I bring a new product to market much faster. And the fourth C is the ecosystem that is encouraged by Cadence. So we are offering a full ecosystem by our partnership with ARM on the CSA as the chiplet system architecture, main architectural protocol for chip-to-chip communication, along with partnering with other standard bodies. UCIe is our main physical interface IP, and also other bodies, bringing together with our SoC design cockpit, which is an automation that we develop and fasten your time from an architectural spec to having an implemented design, whether it's RTL, verification, physical design collaterals, enabling virtual models and emulation models for faster software verification, and combining it with the implementation that we offer from the rich IP portfolio through the EDA tools and flows and to the design services. So if you want to work with chiplets, if you want to build bigger systems, you need to enable architectural sophistication. You need to have a portfolio that gives you the ability to see many different functions and enable many different functions. So as we illustrate here, we kind of differentiate between compute functions, connectivity or interface IP, and the new addition, which is the gray, everything that you need from the system side to support the chiplets. We will dive in a little bit into that later on. So we are either delivering it from Cadence or for the dark gray through partner companies that can offer these IPs. Our Silicon Solutions group started at the lower layer by enabling IPs, and we gradually moved into providing and offering system IPs, memory controller with DDR, UCIe or PCIe controller with their PHYs, enabling DSP and NI solution, of course, with the matching software. And now we are accelerating it to the chiplet side to look more into system-level solutions, into chiplet-level solutions, and this is part of our offering here. If you look at the automotive market, we see that the last decade was a huge jump in the number of, or in the usage of semiconductors within a car. We are expecting to have, by 2030, 60% of the cars as EVs. We have today already, if you look at an average car, between 30 ECUs to over 100 in high-end. We're expecting to have over 200 by 2030. This includes autonomous driving and ADAS systems, includes infotainment systems, and of course, smart vehicle integration. All of this requires more compute, requires more systems, and of course, if we will continue treating all of these as distributed systems, it will continue making the software. And if you think about SDV, software-defined vehicles, all this story becomes much more complex. Okay? Chiplets bring us the value and the ability to have more compute, more functions integrated together into a single system. This way simplify a lot the software management. Okay, now let's take a look at an ADAS example. If I want to bring many ADAS functions that today are implemented on separate compute functions, separate silicons, to the same package, one way to look at it is to build a scalable architecture that supports a family of autonomous or automotive solutions. We offer here a construction of 3 different chiplets to build such an ADAS system. So we have the CPU chiplets which provide the big CPUs for application processing. We have an AI chiplet that is with the Cadence Neo AI IP that is used to do the AI processing, dedicated processing. And in the middle, we have the main base system chiplet, which actually include all the remaining functionalities, which can be sensors and DSP, can be ISP, can be any type of interface and I/O that can serve for the entire system, including memory in the sense of LPDDR, PCIe, other I/Os like Ethernet, USB, and so on. And of course, the system control parts, which I will cover later. With this chiplet framework, you can build different types of systems with different number of chiplets in each system. Of course, it will require different packaging, but the actual die that will be used in each of these packages can be exactly the same die. So with lower effort, you can build more systems. And of course, as I said earlier, this is based on two main components on the chip-to-chip communication. One is the architectural side, ARM CSA and this evolving standard, and the other is the UCIe as the main physical interface for the chip-to-chip communication. Following the previous example, we introduce our Chiplets reference platform. Okay, this is not a product. This is a reference platform architecture and design that we offer to customers to take, license, implement based on. Of course, we are also a design service house. We can do that implementation, but pretty much if you are engaging with this model, you can license and engage with us anywhere from architecture, IP, design services, all the way to tested the silicon parts through our design service house. This chiplet reference platform relies on several main aspects. We have to implement some control functions that used to be part of the SoC level, now split between the chiplets. If you think about security, safety, debug, interrupt, system level controls, you need to have a good system to manage the entire chiplet as if it was implemented on a single SoC. Okay, so the system chiplet is our hub chiplet, it's our main chiplet. This is where the main functionality will reside, but it will be communicated to the other chiplets through the UCIe mainly, okay, with the CSA, and be used there as well. Still, for each chiplet, you also want to have its local control for power, for clock, for reset. You want to have the internal capability to bring up each chiplet for test and debug. Although they are all packaged together, you want to have standalone capabilities in each chiplet. It's not just yet another subsystem. So this principle must be kept as well. And the framework kind of provides all of this as part of the architecture. So if we dive into a specific chiplet, this is how a chiplet will look like. We will have the chiplet control, which is the small portion in that chiplet that is connected to the entire system control and kind of implements the control locally on that chiplet. There is the local control portion, which is the internal control for that chiplet, whether it's control registers, clock, power, and so on. And of course, we have the UCIe, which is the physical interface to communicate with the other chiplets. On top of all of that, we have the red part, which is the unique logic that we will have on each chiplet. So if you look at it, the framework creates the gray and the blue-green parts where you complement it by having the unique logic that you want to have on that chiplet on the red part. This logic can be done by you, by the customer, it can be done by a partner, and so on. Last September, we taped out the first ARM-compliant base system chiplet. If you happen to be on the award ceremony yesterday, you saw that we won, and we are very proud of it. We won the hardware award for this achievement. This is the first demonstration in the industry of a system chiplet. On that chiplet, which we taped out last September, we integrated the chiplet functionality we discussed earlier. On top of that, we had different type of processors, we had different type of system IPs and memory IPs, and of course it utilizes our IP, ARM IP, and our EDA solutions. And the idea is to demonstrate how you can do a multi-chiplet system. We see this as an enabler to the Cadence ARM ecosystem of the future chiplets as I just presented in the reference platform. This was developed obviously in collaboration with ARM, two companies collaborating together to build this, and we will soon have samples to demonstrate also to customers. If it was not hinted earlier, the type of applications that we are targeting with that type of system chiplet and the entire reference platform is what we call the physical AI market, which includes automotive, robotics, drones, aerospace and defense. And if you think about it, all of these systems have a lot in common. in terms of the different IP, different functions you want to have on the system. You need to have sensing capabilities, cameras, you need to have DSP and AI capabilities, you need to have strong compute, and of course, bundle it with strong memory and interface IPs. So they all have things in common. It's very different than the data center or HPC market that usually looking at 3D integration and not 2.5D integration side by side that is offered here. Now I would like to invite Sylvain to talk about the security.
Thank you, Moshiko. So my pleasure to follow this discussion with the security aspect. So security, actually, there are two, you can see it in two different sides. First side, you want your chiplet assembly to not be compromised. Okay, let's call that architecture security, platform security. But also security is constructive. It can bring services. It can bring key management. It can bring to you cryptographic services. I will be talking about attestation. And so it's added value. Okay, so what we want to do, and actually this is one more added value of the Cadence reference, chiplet reference architecture, is to provide you not only all the logic to make your chiplet, but in addition, on top of that, cherry on the cake, you have security services that will be delivered to you. So let me start with the need for securing chips in general and chiplets in particular. Obviously, there can be a situation where one chiplet will be misbehaving. So maybe because it is purchased in some location where you have a hardware Trojan horse inside, or because it will be compromised during the life cycle of the chiplet. So initially everything's good, but then after some firmware update, you get some virus inside of your chiplet, and that's no good. So security clearly along the full product life cycle is something mandatory. Okay, so hopefully we have the solution. Of course, it's not exactly security as usual. There are a couple of constraints. Just to cite a few of them, for automotive market, for instance, we want to boot very fast. Now we have multiple chips, and we don't want that they boot one after the other. Okay, we need parallel boot. We need to build hierarchical trust. So there is a kind of orchestration of the security to be done. Okay, and so we derive from that a couple of security requirements. Some of them are listed here. You see, for instance, attestation, which is really important. Attestation is checking for the integrity during the life cycle in mission mode when the chiplet is updated, checking that it is updated in a proper way, consistent way. Okay? We need to have the ability to be updated over the air. Okay? This is also for compliance with the current regulation about managing the security in mission mode. Okay? So multiple requirements. I can discuss more after the talk, for the sake of time. Just to list a little bit the technology that we have into the secure system in the Cadence chiplets. We implement secure boot. We implement mutual authentication of chiplets, attestation, okay, with different flavors. This comes as a firmware add-on to the chiplet. And for specific markets, we will come with functional safety and automotive cybersecurity. We'll come with anti-tampering. We'll come with compliance to some standards, for instance, making each chiplet have a unique ID provided by PUF. Okay? We have post-quantum cryptography. So all of that is part of the Cadence offering. Okay? So a very rich chiplet platform that comes to you. So I'm co-founder, CTO of SecureIC. We've been recently acquired by Cadence, and this is the reason why we do this presentation jointly today. So we really want actually to complement Cadence portfolio with bringing you in-depth security, easy to use, integrated directly into your chiplet reference designs. Thank you.
We have one more slide, I think.
Yeah.
Yes. So thank you, Sylvain. And we really believe that, security is a very important and key part of the reference platform. And in general, chiplet architecture, we understand the threats that may come from chiplet-based design, and we understand that we have to treat security very seriously, along with other system aspects like safety that is really very relevant to automotive, for example. Again, we believe that with the physical AI challenges that we have, automotive, robotics, drones, aerospace and defense, and the need to bring these complex systems together, we can offer the combination of the new standard chiplet design that we are offering through Cadence, ARM, and the standard bodies, of course, with the Secure IC addition to Cadence. With our SoC cockpit, as I mentioned, this is an automation system that enables you to move very fast from definition of architectural spec on what you want to implement, and of course the IPs that you bring with it, to get very fast the design implementation, enable a virtual platform, enable emulation platform, and obviously, which will fasten software design, but obviously generate also RTL, verification, physical design collaterals, and so on, and getting faster to market, and combining that with the rich IP portfolio that you can get from Cadence with partners like ARM, EDA solutions from Cadence, and our design services along with the chiplet architecture that we just presented. If we have any questions, it's a good time to ask now.
Thank you for the presentation. I had a question regarding the chiplet customization. I see that there's a lot of flexibility in the chiplet architecture, which is provided to the customers. What level of customizations can the customer expect? Because I see there was a chiplet architecture. Can they choose, of course, from the number of processing elements, but can they also integrate their own custom hardware inside it? Just want to get an idea of what level of customization can the customer expect? And also, I guess connected to the second question, since there's the target towards automotive applications, which are very strict in standardizations, and with these customizations, how does it go hand in hand with these standardizations which is expected? So just wanted to hear your thoughts on that.
It is a very good question. Thank you for that. So definitely, this is why it was important to me to mention that we offer a reference architecture. This reference architecture relies on some standards that in order to build or bring any customization, you need to meet these standards, okay? So CSA is a mean to connect between chiplets, UCIe as the physical interface. Obviously, within each chiplet, we communicate with standard ARM interfaces. Can be AMBA, AXI, CHI, and so on, okay? C2C, there are new interfaces now being delivered. So the idea is that you can take this reference platform, you can decide that you want to implement one chiplet differently. Still, you'll have the same interface to the system, but you'll have different set of IPs. You want to do it in a different process technology. It is all possible. Obviously, if you'll integrate different process technology, you need to solve it also on the physical side, like with an interposer, for example, on the package. But we are thinking about that. So everything I mentioned in the beginning, we are building the architecture to be enabler for that. Whether it's multi-foundry, multi-process, different types of customizations. We are not talking about a single reference platform implementation that fits all. Definitely not. But by using that, you can actually focus on where you want to customize, where you think you differentiate, and pretty much enjoy the other types as standard offering. Okay? Thank you. There's another question here. Huh?
Hi, thanks for the presentation. I had a question regarding time to market, because you mentioned it as being also one of the main motivators behind the push for chiplets, to break down the complexity and reuse components more close to the die. So throughout the tape-out process has many steps, and this would help solve maybe some of them. some of them on the initial architectural phase or reusing components.
Right.
But it would add more complexity, the way I see it, on the maybe testing phase, assembly, and packaging side. So how does this trade-off look like? Are we actually gaining time, or are we just pushing the complexity more at the end of the tape-out and production phase?
So this is very good observation, and thank you for the question. It's a very good question. So this is why one of the reasons you see me presenting a 3-chiplet system and not a 10-chiplet system, right? I fully agree that everything that you move to the package integration is potentially additional complexity from the physical design aspect, right? Whether it's different processes, interposers, and so on, as well as the verification validation that it comes with it, right? So you need to be very careful with the technology of today and the next couple of years with the number of chiplets that you are enabling on the system. Maybe in the future, I don't know, in 10, 15 years, you'll have 1,000 chiplets on a system. I don't know, right? Right now, it's very clear that the ideal system, I would say, would be 3 to 5 chiplets, okay? Because, yes, definitely, everything that you move from is inter-chiplet implementation into the chiplet to chiplet is additional complexity and additional push from chiplet design to the package design, and there are many concepts in chiplet design that are now need to be handled at the package level. So package design is also kind of a shifting occupation right now, right? It's a very good observation. This is one of the reasons that we believe in using these standards, in predefining how we want to communicate, but also give each chiplet the standalone capability, because I don't believe that you can miraculously design chiplets and hope that everything will connect and behave together at the top level. You need to have capability to test and debug each chiplet separately. This is one of the reasons we build it this way. So thank you, it's a good question.
Hello, thanks for your presentation. It's really good. I have a question about the debugging module that you presented in your chiplet diagram. Each chiplet actually has a separate debug module, and I'm wondering what's your view or the debugging system at a system level across the chiplet boundaries.
Right. So first of all, debug may be almost the only concept that you need to think both at the chiplet as well as the system level. So I agree with that observation. One of the things we did with our prototype, the September tape-out, is that we built, prior to tape-out, a multi-chiplet system on emulation, and we did a lot of the software enablement and debug on that to increase our confidence in the system. So definitely you need to think of how you enable access for debug perspective on each chiplet, as well as from the system level on any behavior that you want to validate and test and debug across the chiplets at the system perspective. So I agree this is a very important topic to think of. So yes, we are offering a debug component as part of the system portfolio. Of course, it relies on existing debug IPs. Okay, if you talk about ARM, like ARM core sites, okay, so different debug aspects. It depends on the IPs and the functions that you're going to put on the system.
Thank you.
You are welcome to join us. We are at 4219. So you're welcome to join Cadence booth if you have additional questions or talk with Sylvain and me. Thank you.